and welcome back everybody. So in this video I'm going to talk about superposition of solutions. So we already talked about this in our wells hydraulics course, right, where when you have several wells, essentially you can superpose the solutions, or you can take their individual solutions, add them up and find the solution for a well field, for example, for a wells field, for example. So here the principle is exactly the same. I'm just, so a lot of this is going to be repetition of what was said for wells, but in the context of transport of mass transport for contamination. So here's a simple example, and I make the example about a lake just because it's a little more intuitive than an aquifer, but of course this is completely translatable and the same for an aquifer underground water. Okay, so if we have a boat, let's say, going through Lake Michigan or any lake, and we're dragging a song, so something that record concentration of anything, right? Something that's in the lake, and we find, again, this is concentration versus space, so this would be a snapshot, and if we find concentration versus distance that looks like this, it's pretty obvious how many barrels were thrown overboard, right? Let's say there's obviously three different pulses, right? There's three different things that were thrown at different places in the lake, okay? Now, where were they thrown? So if there's, again, it's a lake, so this is just like an aquifer, it doesn't move much, right? Aquifers actually move some meters per day, right? Remember hydraulic conductivity, so usually a decent estimate of velocity or flow in aquifers is about meters per day, is roughly a good number to remember. But here, right, if this is in a lake, we assume this is just a dispersion equation, no advection, right? So there's no net advection. So then the barrels were thrown, at 0, 100, and 250 meters, right? Now, so the question here is, what would it look like if we had all three barrels, right, thrown overboard in the same spot? So the answer is, each barrel here, we have an individual solution. So the mass is known because this is what's in here. You can tell that basically each of the three barrels had the same amount of chemical in it, right? And everything is the same. So if we put all three at the same spot, then all we have is we multiply everything by 3, right? So the mass would be 3 times higher, so the peak would be 3 times higher. And the variance, remember, or the standard deviation, right? Remember that this is just a function of time and dispersion coefficient, right? Sigma equals square root of 2 dt, time, dispersion coefficient. So that wouldn't be affected by the number of barrels. In other words, we would end up with one pulse, right? Let's say it was at 0. So you would have the same variance, but much more, the mass would be 3 times as much, and the peak would be 3 times higher. Okay, but the standard deviation or the variance wouldn't change at the same time. Okay. Now, the bottom line of this, right, is that essentially, you can take a pulse solution, like I described in the previous lecture, right? So if you do the, if you use the pulse solution, the fundamental solution, right, that Gaussian solution for a pulse, and you calculate this for each of those 3 barrels, right? Each barrel being a pulse, then what you end up with is 3 independent solutions that you can actually superpose, or you can just sum together to get, the solution for the case of the 3 barrels. This is really the principle of superposition. Again, remember your wells hydraulics course where we did the same thing for, several wells. So you can see here the individual pulses in different colors, right? So in blue, in orange, and in yellow. And then if you sum them, right? When you sum, you end up with this dash curve, which is just the sum, right? So the dash here is just the sum of the 3 individual solutions. There's a little MATLAB code here just to show you, how you could code this on a computer using MATLAB. So this is what I call PDF means probability density function. So this is just the fundamental solution for a pulse of mass 1. So if you look at this equation here, this is just 1 over square root of 4 pi dt exponential minus x minus ut. So when I say init here is just ut squared divided by 4 dt here, and that's it. This is the equation. So this is how you would write this equation in MATLAB. Of course, you can do this in Excel or any other computing language or software you would like to use. If we start with barrels at 0, 100, and 250, which is what we have here on the left, well, here we have a couple more, but we don't see them in the view. And then you can calculate each individual barrel. So we're doing a for loop, right, for each barrel at 0, at 100, 250, etc. Find the individual. Notice how we multiply by m, right, because here we have 1 instead of m. So we need to multiply by m to get the proper solution for the barrel. And then we can also calculate the sum, right? So we have each individual barrels and we calculate the sum, which is just that dashed line to find the total solution for the 3 barrels. So this is literally the principle of superposition. Now if we write this a bit more, so that was the conceptual, intuitive sort of explanation with, the 3 point sources or 3 barrels, 3 pulses, if you will, and then how you can sum them up. In the math, right, if we write this in the math, having 3 barrels, 3 or 5, right, means you have a function, like the initial condition is a function of space, right? Instead of having 1 pulse at 0, now we have pulses at different places at time equals 0. So the initial condition, right, at time equals 0, the initial condition is a function of space. Again, this is in 1D, so just x. Now that means if we write this into the fundamental solution, right? M equals f of x0 dx0, right? So if we have the concentration is in mass per length in 1D, right? So it's, right? So if concentration is in, say, grams per liter or kilograms per cubic meters, right? Cubic meters is a 3D concept, right? So if we do a model in 1 dimension, we would have to divide this or to multiply this by an area, right, to get mass per length. So in 1D, there's only 1 dimension, so the concentration must be in mass per length, not length cubed. Which means that now we can write the mass as that function of x, the initial function of x times dx, to remove the length scale, right? So it's mass per length times length equals mass. So now we have mass, so we can replace in our fundamental solution. Again, notice that x0 here is ut or vt, whatever you want to call it, right? I've been talking about this in the past few lectures. And now we have a simple solution where we can actually sum for all the little pulses, right? We can sum over, so again, the integral sign here is just a sum, right? Remember that integrating is just summing over a bunch of little pulses. So what we end up with here is the superposition integral where we're summing, right, all these little, the initial function over space, dx, and then the rest is the same, right? So now we have that superposition integral, which does exactly what we just described with the 3 barrels in an aquifer. Okay, in the next lecture, I will talk about convolution, because essentially what we just described is a convolution operation. So I'll describe how we can use convolution to obtain the same, to be able to describe more complicated situations. All right, thank you.